Hey there, Math Explorers. Welcome back. Let's start with a quick question. Have you ever cut a watermelon or maybe a party hat and noticed that the slice sometimes looks circular, sometimes oval, and sometimes just a weird curve? Guess what? You've already created conic sections. Alright, first things first, let's build our cone. Imagine a fixed vertical line, call it L, and another line M that meets it at a point V, but at an angle, let's say angle alpha. Now, if you spin that line M all the way around L, keeping the same tilt, you'll get a beautiful 3D surface called a double-napped right circular cone. The top and bottom parts are called naps, both meeting at the sharp tip. The vertex, that's point V. The line L is the axis, and M is called the generator, since it generates the cone when rotated. And there we go. Our geometric cone is ready. Everything we'll do today will happen on this shape. Alright, first things first, let's build our cone. Imagine a fixed vertical line, call it L, and another line M that meets it at a point V, but at an angle, let's say angle alpha. Now, if you spin that line M all the way around L, keeping the same tilt, you'll get a beautiful 3D surface called a double-napped right circular cone. The top and bottom parts are called naps, both meeting at the sharp tip. The vertex, that's point V. The line L is the axis, and M is called the generator, since it generates the cone when rotated. And there we go. Our geometric cone is ready. Everything we'll do today will happen on this shape. Now let's bring in a flat sheet, a plane. When this plane cuts the cone, the curve of intersection is what we call a conic section. The secret lies in how this plane is tilted. Let's say the angle between the plane and the cone's vertical axis is beta. Depending on whether beta is smaller, equal to, or greater than alpha, we'll get a completely different type of curve. If the plane cuts one nappe, that is, just the top or bottom half, we get one kind of curve. But if it cuts both naps, that's when the real fun begins. The shape changes entirely. So remember, the dance between alpha and beta decides which curve we'll see. Okay, now comes the fun part. Let's see the different curves we can get by changing that angle beta. Case 1. When beta equals 90 degrees, that means the cutting plane is perfectly horizontal. The shape is a circle. Case 2. When alpha is less than beta, but beta is still less than 90 degrees, the plane cuts obliquely and we get an ellipse. Case 3. When beta equals alpha, that's when the plane is parallel to one of the cone's generators, we get a beautiful open curve called a parabola. Case 4. When beta is smaller than alpha, that's when the plane cuts both naps. And boom, you get a hyperbola, a curve with two opposite open arms. So just by tweaking one angle, we've created 4 distinct curves: the circle, ellipse, parabola, and hyperbola. Who knew geometry could be so angle dependent? Literally. Now let's take a closer look at these angels. The cone's generator angle, alpha, always stays fixed. It's like the cone's personality. The plane's inclination, beta, is what we can change, and that's what gives us the variety. When beta is greater than alpha, the plane only cuts through one nappe, giving closed curves like circles or ellipses. When beta equals alpha, the plane runs parallel to the generator, producing a parabola. When beta is smaller than alpha, the plane passes through both naps, forming a hyperbola. So alpha and beta are like partners in a dance. Their steps decide the curve's rhythm and shape. And if they're completely in sync, alpha equals beta, the dance becomes perfectly balanced. That's your parabola. But what if, instead of cutting somewhere along the cone, we slice exactly through the tip, the vertex? That's when we get something special, the degenerate conic sections. Case 1. When alpha is smaller than beta and beta is less than or equal to 90 degrees, the plane touches just the vertex. The section is a single point. Case 2. When beta equals alpha, the plane passes along the generator itself. The intersection is a straight line. That's actually a degenerate form of a parabola. Case 3. When beta is smaller than alpha, The plane goes through both naps at the vertex, giving two intersecting straight lines a degenerate hyperbola. So basically, the same geometry that gives you fancy curves can also simplify into basic shapes like a point or a line, depending on where you cut. It's like geometry saying, cut me wrong, and I'll simplify myself. Alright, math lovers, let's now see how we can actually derive one of these, this circle, using a bit of algebra. We know that the equation of a right circular cone can be written as x squared plus y squared equals z squared multiplied by tan squared alpha. Now suppose a plane cuts this cone horizontally, meaning z equals h. Let's substitute z equals h into the cone's equation. That gives us x squared plus y squared equals h squared multiplied by tan squared alpha. Let's call this equation 1. This equation clearly represents a circle lying in the plane z equals h, with radius r equals h times tan alpha. If h equals 0, the radius also becomes 0, meaning the circle collapses into the vertex point of the cone. And there it is, our circle derives straight from the cone. A perfect slice, no geometry mess, just pure algebraic elegance. Let's wrap it up. We started with a simple idea, cutting a cone with a plane, and ended up discovering an entire family of curves. The circle, ellipse, parabola, and hyperbola, all born from one cone, just sliced differently. When the plane passes through the vertex, we saw degenerate conics, simpler forms like a point, a line, or two intersecting lines. We also derived how the circle's equation, x squared plus y squared equals h squared tan squared alpha, emerges straight from the geometry of the cone. So next time you see a flashlight beam, a satellite dish, or even an orbiting planet, remember, it's all about conic sections at work. And that's the magic behind sections of a cone. In the next video, we'll explore each conic in detail, starting with the circle, its definition, and its equation in standard form. Until then, keep your curiosity sharp, just like our cone's vertex.